My name is Chris Miller. I am the president of the Grand Rapids Amateur Astronomical Association, and I got that all out without tripping over it. Hey, I like that. And it is my honor to open this special meeting that is also sponsored by the Grand Rapids Public Museum and the Roger B. Chaffee Scholarship Fund, who has bringing us this special speaker tonight. You know, our organization, the Grand Rapids Amateur Astronomical Association, exists to, increase participation in astronomy. And thank you for attending and helping to show that, yes, we are making progress towards that goal. And I wanted to say that, this evening is going to be a live demonstration of what a personal commitment to the principles of science and technology, engineering, and math, also known as STEM, that's a popular usage, can make for a successful career. And that's what we're going to hear from our guest speaker this evening. Now, following this, actually coming up this weekend on Saturday, we are going to have another special event, this time with the Grand Rapids Public Museum again, but also with the University of Michigan State University at the James C. Veen Observatory, which is out by Lowell, where there will be hands-on activities, science activities, and demonstrations. And we will give tours of our telescopes that we have there. We have 3 telescopes that belong to the association. And and it's a big if, and it's unfortunately getting worse, if there are clear skies, we would have some telescopic views available. But that particular forecast is now getting very pessimistic, so that portion of it may not be likely. But regardless, there will be things to do out at the James C. Veen Observatory. Now, each year we have public viewing events that take place out of the observatory. They take place every other Saturday, basically. Those will begin on May 13th. That is our next event. And so I will have you check at our website, which is the GRAAA.org, GRAAA.org, for details. Also, if there are last minute, and this is true of any public observing event, we don't know, we hold back on saying that the event is canceled or open until the day of the event. So check on GRAAA.org or your Facebook feed or the Twitter feed for an announcement of whether the event is open or closed or canceled. Anyway, so with that, I now want to introduce the manager of the Roger B. Chaffee Planetarium here at the Grand Rapids Public Museum, Jack Daleski, who will introduce our guest speaker.
Thank you, Chris. So thank you for that introduction. So again, if you don't know me, my name is Jack Daleski. I'm the manager here at the Grand Rapids Public Museum of the Chaffee Planetarium. And today I will have the pleasure of introducing our guest speaker, Dr. Brent Boss. Before I talk about Brent Boss, I would like to talk a little bit about the Chaffee Planetarium and why Brent is here today. So part of it is thanks to the partnership with the GRAAA, the Grand Rapids Amateur Astronomical Association. It's tough to say. But another big part of it is the Chaffee Scholarship. So our planetarium is named after the astronaut Roger B. Chaffee, who lost his life in the Apollo 1 tragedy in 1967. And I think our connection to Roger Chaffee is one of the things that really sets our planetarium apart from other planetariums in the country. And part of the way we honor that is with a scholarship in his honor. And every year, a scholarship is awarded to a high school student who intends to pursue a career in space exploration. This scholarship recognizes leadership potential and outstanding academic achievement in a STEM field. I hope there are some students today who are inspired to explore space. Maybe they'll be inspired by Brent's talk tonight. But even more importantly, I hope there are some who are starting to think about the concrete steps to achieve that goal. Applying to the Chaffee Scholarship is one of those steps, and it is an amazing opportunity. But that is a big part of what we're trying to do here with the GRAAA, with the Chaffee Scholarship, is show some examples of those concrete steps that kids can take for their future. And I think that's really more important now than ever. And I was kind of thinking about even quarantine. And if you took 2 years off of school, I would have been really lost. And I would have been really unsure about what to do with my future and my college career. So we're really thankful to have Brent here, and we're really thankful to have these partnerships where we can show people what the future of space exploration might look like. I'd now like to talk a little bit about Brent Boss. So our guest speaker tonight, he's visiting us from Maryland, where he lives with his wife and children. And I think some of his family is actually here tonight. So we're very happy to welcome them here and that they get to see the show. Thank you. So he lives in Maryland, where he works at the Goddard Space Flight Center. But Brent was born, raised here in West Michigan. And I'll tell you something else. Brent actually visited the Chaffee Planetarium when he was in middle school. And he says that that's what really inspired him to pursue a career in space exploration. So we are really proud of that. And we are really proud to have Brent here tonight. And perhaps he can inspire a young scientist to think about their own future careers. After Brent graduated Holland Christian High School, he attended University of Michigan, where he majored in physics. And then he completed his PhD at the University of Arizona. And at the University of Arizona, he joined the Mars Atmospheric and Geologic Imaging team. And in April 2002, after completing his PhD dissertation, which was entitled Design, Calibration, and Operations of the Mars Lander Cameras, he joined NASA to develop the James Webb Space Telescope. He first started working on the OSIRIS-REx mission in 2010. After NASA headquarters approved OSIRIS-REx in 2011, he served as the systems engineer subject matter expert in optics and visible and infrared spectrometer, optics lead. In August of 2015, he became the TAGCAMS, that's the touch and go camera system, instrument scientist, and continues to serve in that role today. Dr. Boss is also currently the vision systems lead for the Da Vinci Venus Space Probe and the Mars Sample Return Capture and Containment Module. He also supports the Lucy Trojan asteroid mining mission as a subject matter expert. Dr. Boss is credited as an inventor on 31 US patents, and he was awarded the NASA Outstanding Leadership Medal in 2016 for his work as a NASA civil servant. In May of 2016, the International Astronomical Union named asteroid 120285 Brent Boss for his contributions to various space exploration missions. Today, Brent is going to share some of his exciting discoveries that he has been a part of over his 25-year career. We'll learn about some of the exciting things that the future of space exploration has to offer, and we will have time for questions at the end. Can we please get a big round of applause for our guest speaker, Brent Boss?
Thank you, Jack, and thank you everyone for coming out tonight. This is a great crowd. This is awesome after all we went through during COVID. And I'm really happy to be here back in Western Michigan. Like Jack said, I grew up here in Zeeland, and excited to share with you kind of a whole tour of my career over the last 25 years. And so we're going to be touching on a lot of different things. So if you're kind of bored, just hold on a little bit because we'll get to something new very shortly. So like I said, we're going to go back into the past. I'll cover the missions I worked on, particularly when I was a graduate student at the University of Arizona, talk about 2 missions that I'm working on currently at NASA, and then talk about the future, which talking to some students this morning, that's what they were most interested in, like, okay, but what's next? So we'll cover that as well. So tonight we'll be talking about the Mars Pathfinder mission, briefly talk about Mars Polar Lander and the Beagle 2 Mars Lander, and you'll see why it was a very brief coverage of that. And then go into some detail on the Phoenix Mars Lander. And then we'll switch tracks just a little bit. We're going to go from Mars, and we'll start talking about asteroids and talking about 2 missions I'm currently supporting. First one is the OSIRIS-REx asteroid sample return mission, and then the Lucy Trojan asteroid mission. And then we're going to switch gears again a little bit. We'll talk about the future, still talking about asteroid missions, which will be OSIRIS-APEX, and then this Venus mission that I'm very excited about, called Da Vinci. And then finally, we'll end the night back on Mars talking about the Mars Sample Return Campaign. All right, so Mars Pathfinder. This goes all the way back to 1996. I was a graduate student at the time at the University of Arizona, like Jack mentioned, and I had been there for a couple of years, looking around for just the right project to get involved with. I wanted to go to Arizona because they had a really good optical physics program, but they were also very involved in exploring outer space, both from the ground and using robotic spacecraft. So looking around for a couple of years, just trying to find the right group, and finally I found this team that was building a camera for this mission called Mars Pathfinder. So this was the camera right here that this team was building, just an artist rendition of it. It was led by a fellow named Peter Smith, who ended up becoming my PhD dissertation advisor. And I joined the group after the camera was already designed, built, and tested. So this was in November of 1996. The launch was going to be in December of 1996. But they still had a lot of work to do analyzing the data that they had taken of the camera. And I'll talk a little bit more about that as we get further along. Now the mission was, if you remember, was called Pathfinder because NASA wanted to understand and develop 2 new technologies for exploring Mars. The first one was, could you send a rover, so this was our rover on that mission, could you send a rover to Mars and do something interesting with it scientifically? Could you keep it safe that distance away, right? Because you can't control something like this like a remote control car. Because of the time of flight between Earth and Mars, it could take as much as 20 minutes for that signal to get to Mars, and then another 20 minutes to come back. So NASA wanted to prove to itself that you could actually control a rover on Mars and keep it out of trouble, keep from breaking it or getting it stuck somewhere. So that was one of the technologies that NASA wanted to prove on that mission. The other one, if you may remember, was to test out the ability to land a spacecraft on Mars without using retro rockets. So retro rockets can be expensive, heavy, complicated. And one idea was, well, what about if we just put a bunch of airbags around this thing and let it bounce a few times on the surface, and we don't have to deal with all those retro rockets. And so that's what's illustrated right here, is the spacecraft enveloped in a bunch of airbags, cushioning it as it lands on the Martian surface. So sure enough, July 4, 1997, Pathfinder successfully landed on Mars, and these are actual images that our camera took. So our landing site was called Ares Vallis. So here's this is what the rover actually looked like. This was one of the largest rocks near the lander called the Yogi. I'll talk a little bit more about that later. And so this was fabulous, right? Successfully land on Mars. NASA hadn't been to Mars in over 20 years, and we were just ecstatic seeing the images start to come back down. But of course, there was this technology demonstration part of the mission, but those of us on the camera team were really trying to figure out how much science we could actually extract from this mission. So one of the key science goals for Mars exploration is to follow the water. So that's a mantra that NASA uses, because the idea is if you follow the water, you might have a chance at detecting either present life or past life, which would be a huge scientific discovery if we could prove that life exists or has existed somewhere else besides Earth. And so one of our main goals, science goals of the mission, was working with the geologist we had to try to prove whether or not liquid water had once flowed through this area of Ares Vallis. Because from orbit, there was some indication that there may have been water altering the surface. And so the geologists we were working with were really trying to understand the images. What were they seeing? And for these rocks that were close in, you could do a pretty good job. You could tell, are they smooth? Are they angled in a certain direction? Have they been altered by water? But unfortunately, unlike the rovers we have nowadays that are much more capable, all of the complicated science instrumentation was actually on the lander. We only had one science instrument on the rover itself. And so from a camera standpoint, we couldn't take our camera and move it around and get to things like we can now on Mars. So what I spent most of my time doing was taking all of that data that I was given when I joined the team and trying to extract as much information out of it. And to do that, what you do is you remove all the things that weren't caused by the Martian scene. So you're trying to remove things caused by the lenses, caused by the detectors inside the camera, in some cases caused by cosmic ray activity that's just always hitting Mars. And so I'll just give you one example of that. One of the things we were very interested in from a geology perspective were these two features here. These were called twin peaks. So this is North Twin Peak, South Twin Peak. And when we got the first images down from the mission, the geologists were saying, well, it looks like there may be evidence for water here, but there's some linear features we would like to see better over here as well. Is there anything you can do to help us understand what that looks like? And so that task fell to me, along with trying to understand anything else out here that we actually couldn't get to. So I'll just show you one example of what you can do if you did a really good job of calibrating and testing the camera on the ground. And then as long as the camera doesn't change, once it gets there, you can remove everything that's not coming from the Martian surface and get a better idea of what it looks like. So I'll just show you the South Twin Peak example there. So you can see how much more detail you can bring out. In fact, you can kind of compare the texture you can see on these rocks and these things that are a few feet away are pretty comparable. And we were able to bring out some features here that look like, you see this bright line and the darker line. There was some indication that that may have actually been caused by water coming in here at different levels and creating these terrace-looking features. And of course, we could see rocks further out here on the horizon as well. So spent a lot of time doing this, trying to improve the images so that we could understand if liquid water had actually flowed here at one point in time. And that was a lot of fun. But that was not our main job. Actually, the main reason for having our camera on the mission was to help the rover team successfully do their job. So I have several of the images that represents the types of images we took. So these are all pretty raw images we took from the camera. And we had to help the rover team make sure they didn't get this thing stuck, make sure they didn't break it, and then also help them navigate to the most interesting parts of the landing site in Ares Vallis. So I won't go through all of these, but I'll start with this one up in the upper left here. This was taken a day after landing, and we had two ramps on the lander that we could use to roll the rover down to the surface. So we took a look at both ends and said, well, this end over here is the safest, and we deployed this ramp so you can see it coming down, and there goes the rover down the ramp. Then once we had our Mars legs under us, right, for a couple of days, and we started to try a little bit more elaborate things. So that big rock I was talking about earlier, Yogi, that's what's shown over here. The rover team said, okay, let's try to get a spectra off of that. So the only instrument on the rover was an alpha proton X-ray spectrometer. And in order to get a spectrum using that kind of spectrometer, you have to get up right against the rock. So you can see, the camera we had was a stereo camera. And that allowed you, if you took images through both eyes were about 12 inches, about a foot away from each other. If you take images in both of those eyes, you can develop a topographic map of the landing site. So we surveyed the whole landing site, built up that 3D map, and then gave it to the rover team. And they used that to try to navigate up to this rock. And you see, they did a pretty good job, but they just kind of missed it. The rover rolled right up the edge of Yogi, and the spectra we got back was nonsense, didn't make any sense. So we backed the rover off, we took a few more images, made the topographic map a little more accurate, and then a couple of days later we were able to drive right up against it and finally get a decent spectra off of Yogi. And that was the main science objective with the rover, was to take these spectra of various interesting rocks. So here's another example. The spectrometer could actually articulate down, and we could go and measure rocks that were half buried in the surface as well. And then as the mission wore on, we got a little braver, at least the rover team got a little braver, and we started to test out the rover to see if it could handle the type of terrain where we had landed, because that was one of the real things the rover team was interested in. They had designed these 6 wheels to be able to go over and not get stuck rocks that were about the size of the wheels themselves. So here you can see later in the mission, we started to tackle things that were a little bit more challenging. You can see it went over some pretty good sized rocks, didn't get stuck, and didn't break itself. So this was all fun and exciting at the time, but in reality, the rover didn't go that far. If it had an odometer at the time, it would have only read about 330 feet. And it only got about 41 feet away from the lander. But it did prove out that we could successfully operate a rover on Mars and also measure and do things interesting scientifically. And at the time, it was a huge deal. We were blown away being a part of the mission, just how much attention we got, not just in the country, but around the world. And I think part of the reason for that was my boss, Peter Smith, had said when he won this mission, or when he won the camera to go on the mission, said, we're going to share this data as soon as it comes down from the spacecraft. We're going to put it right on the web. So this was 1997. Remember, the World Wide Web was only a couple of years old at that point in time. And it's very different than the way most of our lead scientists handle their data. Usually when they get selected, it's a big conversation, a negotiation between headquarters and the lead scientists as to when they're going to make the data public. And most of them will hold on to it for as long as they can, up to 6 months, sometimes even up to a year. And Peter said, no, this is funded by your taxpayer dollars. Everyone should be able to see this pretty as quickly as they come down. And so we put the data into a format everybody could read. And it was so popular that it brought down the JPL site from the traffic. And we had to set up mirror sites at the University of Arizona. And so we ended up making the cover of Time. These are our images on the cover of Time magazine. The Postal Service came out with a stamp for us. Mattel made a Hot Wheels toy. This is my personal copy with people's signatures from the team on it. And it was really neat to be a part of that, to know not just the country was following us, but around the world. And it really became part of, I think, the pop culture consciousness of what a Mars mission is. And so a couple of years later, we started to see our mission just show up in these different areas. So in 2000, there was this Red Planet movie here's Val Kilmer. They're not wearing space helmets, obviously, by the way. But they used the rover to make I think that they had to use the radio in the rover to make contact with somebody. And then a year later, if you're a Star Trek fan like I am, Star Trek Enterprise, if you remember, came out in 2001. And they had this really inspiring intro sequence with this really nice song, and they showed all these key moments in human exploration. And then they get to space exploration with the first spacewalk, Neil Armstrong touching down on the moon. And then they include Mars Pathfinder, which was really awesome too. And then they used our images. These are our images, even cleaned up a little bit more for Hollywood. And then probably most recently, there was the movie The Martian. I didn't read the book, but I saw the movie. And stranded astronaut Mark Watney had to use the lander to reestablish contact with Earth. And in fact, he used our camera to do that, if you remember the movie. And they did a fabulous job, the producers of the movie. Here's an image of what our lander really looked like, taken from kind of a crappy camera that was on the rover, but it's a composite. And you can see they did a really good job of representing the lander. And in the movie, they made the camera operate very realistically as well. There were only a few errors that they made. I was pretty impressed with how they did that. So it's fun to see this every now and then. You'll still see a Pathfinder reference come up all the way from 1997. Now, in terms of the science, probably the most important thing is we did feel like we could come up with enough evidence that there had been liquid water that flowed at the Ares Vallis landing site, mainly from the observations of a lot of rounded pebbles and stones in the area, as well as some indication of imbricated rocks out on the horizon. We never did claim those features on the Twin Peaks were necessarily caused by water. We couldn't be definitive with it. We couldn't get topography off of it because that feature was a kilometer away, so a little more than half a mile away, and our stereo baseline wasn't large enough to be able to get 3D information off of that. Another interesting result from the camera was we proved that Martian dust is actually partially magnetic. So we had these targets on board the lander with magnets set behind these steel plates. And these magnets all had different strengths. And we would take an image periodically as the mission went on, and over time we could see dust start to adhere to them. And so the iron oxide, right, the thing that makes Mars that red color, part of that material is actually magnetized. But probably the most exciting thing, at least I thought at the time when it happened, was the discovery of dust cyclone, dust devil activity at the landing site. And that's what these images show you here. And the interesting thing about this, actually, much to the chagrin of Peter and the rest of us on the imaging team, the first one was not discovered by us working the mission. It was actually discovered by an Earth geologist named Steve Metzger. And he was downloading those free, publicly available images just like everybody else was. And he was analyzing them just like he does his images that he takes on Earth, because he's interested in dust storms and cyclones and how they alter the geology of Earth. And he processed one of the images and said, hey, I think there's a dust devil there, and contacted us. And sure enough, when we went back and looked for the data and, in fact, enhanced the data, we started to see a lot more activity. And we looked through all the instrument data and ended up finding out we had simultaneous measurements in some cases of this dust devil activity. And this was exciting to me, especially back then, because when you think of astronomy or planetary science, you know things are changing, right? But they're changing over thousands of years or even millions of years. And here we see activity on Mars changing things in a matter of minutes in a very dynamic environment that you typically don't see. So it was very exciting for us. But probably the biggest legacy, of course, is the fact that we proved to ourselves and we proved to NASA headquarters that you could do something useful on Mars with rovers. And so the real legacy of Pathfinder is what we've been able to do since then. So here's an Earth version of the Sojourner rover. And then this is the kind of rover we sent to Mars in 2003, Spirit and Opportunity. And then most recently, we've sent the Mars Science Laboratory, or Curiosity, and then Mars Perseverance, which I'll talk a little bit more about later, and just landed in 2021. So this was a great mission to be a part of, certainly a highlight, my first mission, and it was just an amazing experience. And unbeknownst to me at the time, that was going to have to sustain me and the rest of the team I was working with for several more years after that. Because the very next mission in the queue, the next mission to go to Mars in 1999, called Mars Polar Lander, which this time we had 2 cameras on board, unfortunately, we crashed on Mars in December of 1999. And then the next mission we sent to Mars, which is called Beagle 2, crashed on Mars on Christmas Day, 2003. And I include this in here because this was a big part, actually. I had 3 years invested into Mars Polar Lander. I had 5 years invested into Beagle 2. And they all launched successfully, but they didn't land successfully. And to this day, it's still the most difficult thing I've gone through from a professional standpoint. I had invested a lot of time into it. I had a big part of my PhD dissertation was tied to Polar Lander and getting data back from the mission. And so this was a picture taken by a Los Angeles Times photographer at the time, and the angst on my face was just a fraction of what I was feeling inside when the landing day came and went, and we didn't hear anything from the lander. Same thing with Eileen. This is Eileen Yink. She's actually from Western Michigan as well, from the South Haven area, and we were office mates at the time. And so I bring these failures into everything I've done since then, and it really drives home the point that it's a very thin line between success and failure in these missions. And in fact, Beagle 2, which is shown here, this was a British Mars lander as well as partially funded by private funds. It almost made it. It almost worked. About 11 years after the mission failed, we had a spacecraft fly over the landing site called the Mars Reconnaissance Orbiter. And it has a high-resolution camera on board that can resolve things in certain orbits to about 2 feet. And this was an image it took. We finally saw that, wow, we almost worked on Christmas Day in 2003, because we can see a few of these petals, so this all thing folded together And it's about the size of a saucer sled you might take down the hill here in the winter time frame. And you can see that it started to unfold. There's 1 petal, 2 petals, maybe even 3 or 4. But unfortunately, it all had to unfold in order to make radio contact with either the Earth or Mars Express, which was its radio relay. So again, I just bring this out as you think about these kinds of things. You have to know this can always happen, and you keep that in the back of your mind every time you're trying to design these things and design a mission to figure out how can we improve our chances of success, because believe me, if you've ever gone through this, you don't want to do it again. Fortunately, while we were going through all this, Peter, our boss, was still working on yet another mission, and he decided to try to take the lead of an entire mission, not just instruments, not just cameras. But he came up with this idea for the Phoenix Mars lander. And this was all being put together just as I was finishing up my PhD dissertation. And Peter's plan was to fly this spacecraft called Phoenix, fly it to the northern polar region of Mars, which recently had been detected. There appeared to be a large reservoir of water ice just below the surface. So again, follow the water, the Mars exploration mantra, right? So one of the questions is, okay, it looks like certainly Ares Vallis had a flood go through. From orbit, we see other indications that there was liquid water on Mars at one point in time, but where did it all go? Did it escape to space? Is some of it still there? So the goal of Phoenix was to fly to the northern polar region and see if it could confirm that observation from orbit. There was still a lot of water ice there. So we had a robotic arm that would allow us to dig down into the surface, and those of us that were still working cameras, we had 3 cameras on board. We had a real close copy of the imager for Mars Pathfinder, except it had better detectors. We had a robotic arm camera mounted near the wrist of the robotic arm, and then we also had an optical microscope, which was almost a direct copy of the microscope that we flew on Beagle 2. So we launched Phoenix in August of 2007, and fortunately landed successfully on May 25 in 2008. And it didn't take very long for us to be excited. Of course, we were excited about the landing, ecstatic for those of us that had lost several missions in a row at that point. But the other thing to be excited about was it looked like the water ice we had come all that way to try to confirm was there wouldn't be hard to get to. Because one of the things we had to do right after we landed was we wanted to confirm that we were safely down on the surface. So we wanted to get images of the 3 footpads from the lander and make sure we weren't on a rock or going to slip off into something as we started to dig into the surface. So with the camera mounted on the deck, we took a picture of 1 pad, but we couldn't see the 2 other ones. So we had to take the robotic arm and with the camera peer underneath the lander. And these are the images that we took. And it shows good news, right? We've got footpads safely down on the ground. But then, wow, what's this other stuff we see underneath there? And it looked like our descent thrusters had actually excavated some of the landing site for us, revealing water ice just a few inches below the surface. So this obviously, when you look at that, that looks, that's what you would think a solid chunk of ice would look like. And then even looking over here, you can see it's nice and smooth, it's highly reflective. These holes were directly underneath the descent thrusters. And it looked like, in fact, a chunk of ice had gotten blown out by the thrusters at that point. So this was early on, right? So Sol 4, so we call Mars days sols because they're not the same length as Earth days. They're about 45 minutes, a little under 45 minutes longer. But less than 4 Mars days into the mission, we think we have pretty good proof already that we're not going to have to dig very far. That was really good news, because one of the things we were worried about when the mission was being designed was we're going to go to Mars, we're going to dig and dig and dig and dig for months and never get to the water ice. And in fact, we made the robotic arm as long as we could just to try to mitigate that risk. But already by the 4th and 5th day, we were feeling like this is going to be easy. This is going to be a piece of cake. So on Sol 7, Mars Day 7, we took our very first dig sample using that robotic arm and took these pictures with a robotic arm camera. That's what the RAAC stands for. In fact, these were pictures I commanded and processed. And you can see in here, look, it looks like those little flecks of this white material. Now, we weren't calling it ice yet, because it could be other things. It could have been some kind of carbonate. It could be some kind of salt. But, we kind of felt like this is really water ice sitting there. And by Sol 11, we thought we were ready, anyway, to try to get our first water ice sample into an in situ instrument called TIGA. And the sample is called Baby Bear. And it looks like it's going to be a piece of cake, right? A big chunk of water ice to put into TIGA. And TIGA was the instrument that would really allow us to analyze the mineralogy and the chemical makeup of whatever we put into it. And when we thought about planning the mission, we had a very elaborate process for deciding what things do we put into TIGA. We wanted to make sure we put just the right samples in there because we only had 8 cells that we could use to analyze material. So you just didn't want to willy-nilly just put stuff into it. You want to be very judicious about what went in there. Well, with the first sample with Baby Bear, we were very careful. And by the time the days passed and time went on and we checked out TIGA, we put the sample in there. It ended up being pretty uninteresting. All the interesting stuff looked like it was already gone. We just didn't see anything. There was a little bit of liquid left, but nothing like we had expected. So it was pretty disappointing. And so, we were kind of scratching our heads a little bit about how are we going to get a good sample into TIGA. But while we were doing that, anytime we had the opportunity and we weren't digging a trench, we would go and we'd take the cameras and we would look at these white patches that we had undercovered, both with the robotic arm camera and this SSI camera, which was our main camera on board the lander. And this was a trench we finished digging on Sol 20. And so you can see a lot of white material in here. I'll direct your attention to these 3 white chunks here. These are about the size of dye from a game. And so we dug that trench, and then we started to go dig other trenches. We dug, in the end, 12 trenches during the mission, but we'd always go back and image when we could. On Sol 24, we went back and imaged, and where did these things go? And in fact, you could see even changes up here. And so at that point, we knew this wasn't some kind of carbonate, this wasn't some kind of salt. This was, in fact, water ice. And what had happened to these chunks, you don't see little pools of water here, because on Mars, the atmospheric pressure and the temperature can't support liquid water on Mars. And so that solid ice directly sublimated into the atmosphere, just like dry ice does here on Earth. And it was at that point, less than a month into the mission, we said, yep, there's water ice there, and it looks like there's a lot of it, and it's not far down. So we called a big press conference. All the reporters came in, and it was a big day for the mission. I think we were front page news that day, because now water wasn't just flowing on Mars in the past. There was water still there, which is important, both from the life standpoint, but also if you want to send a human crew to Mars, you want to have a nice reservoir of water. Unfortunately, from a NASA headquarters standpoint, they really wanted to understand better what this water was. And for full mission success, we had to get a water sample into TIGA. And that proved to be really, really difficult. And so in the end, we threw out that playbook where we were really careful, digging and really analyzing it. And we started to try to do this blind because we just weren't successful using the ways we had planned to do it on Earth. And this, in fact, shows one of those blind attempts. On Sol 60, we thought we had something easy to dig into, put into the TIGA. So these are the doors, actually, of the TIGA, and the material would go through there. In this case, we didn't deliver anything because we tried to do it all blind without even being sure we had a sample. So this took a lot of work. It took a lot of finesse, really, because the material, the Mars soil, or the regolith, as we call it, it behaved very differently than anything we had done on Earth. And so it really threw us for a loop. But finally, on Sol 64, we finally got the Wicked Witch sample into TIGA, and these are actually the raw data. So this is a calorimeter result. This peak right here is consistent with water, and then this is a mass spectrometer result, and this dip here is consistent with water. So at that point, we could finally declare success from a NASA headquarters standpoint. And we called the reporters all in again, and the TIGA lead got before them and said, there's water ice, this is water ice. And they all said, yeah, didn't you tell us that like 40 sols ago? They didn't really get it, right? But it was a big day for the mission because headquarters really wanted us to be able to better analyze what was there. Another thing we know, like I said, we had everywhere where we saw this interesting white material, before we really were sure it was water, we were doing change monitoring and we were watching it. And those images that were there, that we took under the lander, we kept monitoring those too. And as we started to get more of those images back, we started to see activity that made us think maybe it's not just water of solid ice stuck to the struts. it might be a mixture of water ice and water, or water all by itself, which it shouldn't happen, right? Pure water can't exist on Mars, which is true. But what we did is we started to research and look into the literature. And somebody, actually, Haberle et al. In 2001, had published a paper that said, yeah, liquid water can't exist on Mars in its pure form, but if you mix enough salt into it of the right kind, it actually can be stable on Mars. So then we started to do the calculations and started to look at these images. I'll play through these here. So probably the best evidence that some of this is actually liquid water is on that strut right there. And if you'll watch, you can look at these, but also look at what happens along the rest of the strut as well. And it looks like some of these particles are actually growing in size. So the thought is that it's sucking the water vapor that's in the little mini atmosphere below the lander, and they're growing in size. Some of these may also just be liquid water, and they're just also getting bigger. It looks like some of them merge together. It looks like some of them are pulled by gravity over the slope of the strut. And so this was really exciting. Some of it was, it was a little controversial within the team. You kind of bring your own prejudices to the images once you start looking at them. But once you do the calculations, you find out, yes, it is, even if the images aren't conclusive, you could have liquid water. And then after the mission was finished, some of the other folks on the team looked back other places where there was this white material, and it looked like in spectra that were taken of that, it was also consistent with liquid water, which was pretty neat, because up until that point, there really hadn't been the idea that you could have liquid water, even a brine, on the surface. And since then, we've also seen what look like breakouts of brine coming through the surface that we've seen from orbit. So Phoenix ended up just being a very successful mission. And for those of us that had lost several missions, particularly the polar lander mission, it was kind of vindication, right, for what we had gone through. And about a quarter of the team were old Mars polar lander folks. And so really felt like we kind of had a second chance in the universe to run our experiments, because this was very similar to the goal of Mars polar lander. I already talked about the different observations we made of the water ice, and also potentially liquid water or brine being there. In the end, probably the most surprising thing from the mission was the discovery of perchlorate salts in the surface material, and also the water that we picked up. And so we were successful later to get more samples of the water ice into TIGA and analyze them with a little bit more care and precision. In fact, we had another instrument called WICL on board that lent itself to that. And that was surprising, because perchlorates mean that liquid water flowed here and not too far even in the geologic past. So another indication that there was water once everywhere on Mars. All right, so now we're going to leave Mars for a little bit. We're going to move to present day and talk about some asteroid missions. The first asteroid mission I'll talk about is the OSIRIS-REx asteroid sample return mission. And this is a mission that's getting close to its end. It launched in September of 2018. And the goal of OSIRIS-REx was to fly out to this body, which is a near-Earth asteroid called Bennu. And Bennu is not really big from a planetary perspective. It's about 1,600 feet in size, so a little bit bigger than the Eiffel Tower or Empire State Building. But the reason OSIRIS-REx wanted to fly to it was it looked like it's a carbonaceous asteroid. I mean, it has carbon-bearing minerals on it and potentially organics. And one of the reasons this is interesting scientifically is that one theory is that the life that was formed on Earth might have been seeded by material like this coming from asteroids. So in the early part of the solar system, the thought is bodies like these collided with Earth, left organic material from which life sprung. And so our goal was to fly out here, study it for 2 years, try to see if we could find the most carbon-rich area on the surface, and fly down and grab a sample of it. Oh, and also not break the spacecraft. So we had to find a safe landing site as well. So I'll help you orientate yourself just a little bit. This is how I figure out where I am when I'm working on Bennu. So there's this big rock right here. We'll let it go around one more time here. Okay, so here it comes. So there's this big rock. You've got some craters. And then after it rotates about 90 degrees, our landing site we chose was up in here, up north near that polar region. So I have a map. and maybe a little easier to see. So here's that big rock I was pointing out earlier. Here are those craters. We ended up studying 4 potential landing sites. We named them after birds. So sandpiper, osprey, kingfisher, nightingale. This is the nightingale site we chose up near the pole. It had a lot of carbon-bearing minerals in it, and it was also safe. We could land there without breaking our spacecraft. And so here's a close-up picture of that. So this circle right here, this yellow circle, that's 12 inches in diameter. That's the size of our sample head that we would capture the sample in. And the things we're trying to avoid, right, are these big rocks right here. We don't want to land on those. It would tip us over, crash us into the surface. We don't want our solar arrays to nudge up or hit these as well, because that's how we generate power for the mission. And so our goal was to hit that spot right there. So what I'm going to show you next are a series of images from that sample acquisition maneuver from a camera called SamCam. And so this is looking right down our sampling arm. The sampling arm is called TAG-SAM for the touch-and-go sample acquisition mechanism. And the part that collects the sample is this circular head right here. You can see it kind of squares itself up against the surface right before we make contact. And this works kind of like a vacuum cleaner in reverse. Instead of sucking in air, it actually blows out nitrogen gas, which forces material into the inside of that head. And you can see as we made contact, Bennu hardly pushed back at all. We just kind of flew right into it. And we kind of likened it to when you jump into a ball pit, like a kid's playground area. There's just no strength to this surface. So I'm going to show you another set of images. These were taken by one of the cameras I was responsible for, and it will show you a little bit more of the contacts, all the way from orbit until we back away. And so here's that big rock I was showing you earlier. You can see the craters come up here. There's one. So we're still in orbit, and then you'll see all of a sudden a change. That's when we made our deorbit burn on the spacecraft. There we go. We did our burn. And now the spacecraft is actually using these images to figure out if it's on the correct trajectory to get to the sample site, which is right in here. So that'll go out of the frame shortly, but you'll be able to see the shadow of the TAG-SAM arm right before it makes contact. So here comes the shadow. And boom, we make contact. And we just made a mess of things, right? And then we started to back away, and this whole cloud of dust just kind of tracked with us, kind of like Pigpen in the old Peanuts cartoons as we backed away. And this whole back away period was actually 2 minutes long. It's running faster than it would in real time. So we continued to back away from Bennu at that point. We didn't go back into orbit around it. And we took a picture of the inside this time of that sample head using SamCam again, and it was good news and bad news. The good news was we had gotten a lot of material. The bad news was we had gotten so much that the flaps that were supposed to close to keep that material in place were actually wedged open, and we were leaking material into space. And so very similar to the issues we had with Phoenix and sampling the water, we threw out this extensive playbook that was going to take a whole week to study the sample, figure out how much we had, decide whether or not did we like this sample, were we going to put it into the sample return capsule. And we threw out the playbook and decided we've got plenty of sample, let's get it safe before we lose more of it. And we condensed that week-long activity into a little more than 2 days, working around the clock. So I'm going to show you another series of images from another camera that I was responsible for, and it shows us stowing the sample. So these are images from a camera called StowCam. This is the side of that sample head, and we latch it into place here. You can see some of the material escaping as we did that. And then once it was in place, we pulled back on it to make sure it was securely inside the sample return capsule. Once we did that, we blew an explosive bolt on the wrist, pulled the arm out of the way, and then closed up the SRC. And so again, this all took place a little more than 2 days, actually during the height of COVID as well. So this was in October 2020. And pretty much everything you see in this image here is what's going to come back to Earth. It's just part of the spacecraft that will come back. So all of this here, the orange part, the white part, that's the sample return capsule, or the SRC, and that's going to separate once we get close to Earth, and it's going to land via parachute in the Dugway Proving Grounds in Utah, September 24 this year. So once we had the sample safely in there, we could catch our breath a little bit and feel like, we were kind of out of the woods. So once we did that, we took a look at all of our telemetry. We took all the camera information together, And we worked with some animators to put together what it looked like if you were on the surface during this sample acquisition event. And this is our best faithful representation I can show you about what it probably looked like if you were a resident of Bennu that day. So this is a better example of the speed. We were going pretty slowly to the surface, about 2 centimeters per second, so kind of like a slow walk. And in fact, the spacecraft never sensed that it touched down. The surface was so weak that it just never tripped the sensors that we had on the arm. And in fact, the only reason we acquired a sample and backed away from the surface was we had a contingency plan on board which said, look, spacecraft, you know what time you're supposed to touch down. If that time comes and goes by about 10 seconds, go ahead, release the nitrogen gas, collect the sample, and then 10 seconds later, go ahead and burn your retro rockets and just get out of there. Because we were worried while we were planning the mission for just such an event that we would bury ourselves into a weak body and never be able to get ourselves back out. And in fact, that's what happened. So, yeah, very exciting time for us. And we left Bennu in May of 2021. So we've been on our way back to Earth for almost 2 years now. We got a lot of sample. We think we've got almost a pound, a little more than 3/4 of a pound of material, a whole almost order of magnitude more than what NASA headquarters said we had to go get. Everything's going well with the spacecraft thus far. The SRC is coming back September 24, if it's good or not, because that's all determined by gravitation. In terms of the key science to date, I already talked about the carbon-bearing material we observed. That's why we went to the landing place we did. We think we got a carbon-rich, potentially organic-rich material that we'll be able to analyze here in laboratories on Earth. I already talked about just how weak the surface was, which wasn't a total surprise, but when you look at it, it just looks like a rock, right? You wouldn't expect it to just give away once you touch it. But probably the most exciting science discovery to date, at least from my perspective, was we determined that Bennu is an active asteroid, which was a big surprise at the time because it's not asteroids that are supposed to be active, it's comets, right? As they come closer to the sun, they heat up, they develop an atmosphere or a coma. It typically doesn't happen with asteroids. Asteroids are supposed to be dead. And at this point in time, there are only a couple of other asteroids known to be active. But soon after we got into orbit around Bennu, we were taking pictures with one of my cameras. This was taken by Navcam 1. And we would take about a dozen images a day just to make sure we were on the right trajectory. And then when we were actually we were on a skeleton crew because of a government shutdown during the Trump administration. We got images down that looked kind of odd. I mean, we could see Bennu, but we also could see something weird happening here. And we said, what in the world is going on there? We weren't sure what it was. It kind of looked like Bennu was releasing material, but we had to be very careful about this because, again, this is highly unlikely. You just don't see this off of asteroids. And so kind of like I did on Pathfinder, we had to really process these images. We took out all the effects we could think of that were caused by the camera, had to take out cosmic rays, had to take out stars that were in the background here, removed all of that from the images. And once we did that, we still had something that looked like Bennu was releasing material. And so we changed the way we actually operated the mission to look for this activity because it was just so interesting. And sure enough, once we started to look for it, turns out Bennu is ejecting material on an almost daily basis. Anytime we went and looked at it, we could see material like this. Some of it leaves Bennu forever, never comes back. Some of it you could see actually leave the surface, come back, re-impact the surface, and create another ejection event where other material flies off into space. So until we get the sample back and we can analyze the Bennu material in a lot more detail here on Earth, this is probably still the most surprising thing thus far from the mission. And again, September 24, that's when the sample comes back. It'll be in the press. You'll be able to follow along. All right, the other mission that I'm currently supporting is another asteroid mission. It's called Lucy. It's a mission to the Trojan asteroids of Jupiter. And the Trojan asteroids of Jupiter are these asteroids that are left over from the early formation of the solar system. We believe that these gravitational equilibrium points are where the planetesimals that made up the planets, at least the terrestrial planets, so like Mercury, Venus, Earth, and Mars, the leftover remnants from that have coalesced in these gravitational equilibrium points, and they follow Jupiter around the sun and also precede Jupiter around the sun. And so the goal of Lucy is to go visit these objects because we don't know much about them in any kind of detail. And the mission has just gotten started. We launched in October of 2021, but it's going to take a while to get to that first group. First, we have to do 2 Earth gravity assists to give us extra energy and to perturb our orbit so that we can fly out first to that leading group of bodies. So we get there in 2027, August 12. We're going to visit 5 of those. And then in 2028, we got to fly all the way back to Earth, do yet a 3rd Earth gravity assist, which will slingshot us out to this trailing group, which we'll encounter on March 3, about 10 years from now. And in that second group, we'll be visiting 2 of them. And we won't go into orbit around any of these bodies. These are just flybys. So most of the really good, the juicy data we'll get over a period of a couple of hours. But we'll be doing observations a few days before and a few days after we encounter each of these bodies. We can't go into orbit around them because we just don't have enough fuel to be able to do the burn and go in orbit. This is what we think these asteroids look like based mainly on radar observations from the Earth. So the first asteroid we'll visit is Eurybates, and it actually has a very, very small moon that you can't see at this scale. So we're going to take credit for visiting 2 asteroids when we visit Eurybates. And then less than a month later, we'll be flying by Polymele, and then Lucas, and then Oris, and then we fly all the way back to Earth, do another Earth gravity assist, shoot us back out, and then we visit Minutius and Patroclus, which are actually orbiting each other. So that's a really interesting system that we'll be studying, and it's kind of the highlight of the mission. On the way out there, we're also going to fly by 2 near-Earth asteroids. One is called Donald Johanson. That's just a main belt asteroid, not particularly interesting, but it's on our path, so we'll be trying out our imaging techniques and our spectrometers and things like that. And then after we launched, there was actually an asteroid discovered that is along our path. And we're going to visit that one this year on November 1st, so you'll probably see some of that in the press as well. But today, we've launched successfully, which, the odds aren't always in your favor there, but we're in space, we're operating well. We've done 1 Earth gravity assist back in October thus far. We came really close to Earth. We kind of skimmed the atmosphere, flew by closer than what the International Space Station orbits and the Hubble Space Telescope. And we tried out our instrumentation just to make sure everything was working. This is probably the neatest thing we took. This is an image, a composite image of the moon we took with a camera called LORRI. And so that was back on October 16. So this gives you a little flavor of the type of information we'll be able to get back from the Trojan asteroids. All right, so now we're going to jump ahead a little bit. I'm going to end the night talking about the future missions that we're currently working on and preparing at the Goddard Space Flight Center. So the first of those future missions is called OSIRIS-APEX. It's another asteroid mission. This is what we're going to call OSIRIS-REx after we successfully deliver the sample on September 24, because the spacecraft will be perfectly good still at that point. We'll have plenty of fuel on board. All of our instruments are operating just fine. So after we deliver that sample, the job of OSIRIS-APEX is to continue on its journey around the sun and rendezvous with another near-Earth asteroid called Apophis. And so here's kind of an artist's rendition of Apophis. And what's interesting about Apophis is when it was first discovered, this was one of those you read about in the newspaper being the doomsday body, right? The one that's going to knock out life on Earth. And until they refined the orbital calculations, that was true for a little while. But in April of 2029, it's going to make a real close flyby of Earth, less than 20,000 miles away. And this is what we think Apophis looks like, again, based on radar observations. It's a little bit smaller than Bennu. It's about 1,100 feet across. It's kind of more of a peanut shape than a walnut shape, like Bennu was. But it's going to fly by so close, it's not going to break up. It's not below what's called the Roche limit, which would break up the asteroid. But it's going to fly within the resurfacing limit of Earth. And so the job of OSIRIS-APEX is to rendezvous with Apophis a few weeks before it gets to Earth, study it, characterize it, see what it looks like before it passes by Earth. Because when it passes by Earth, it's going to be so close that the gravitational force, it could change the spin axis of the asteroid. It could change the rate at which it rotates. It may also even redistribute material on the surface. It could move rocks around. And so the goal of OSIRIS-APEX is to watch that happen. So we'll be following it during that flyby, and we'll remain in orbit around it to see what happened after it did that close flyby of Earth. And we've never done anything like that before with NASA, so it'll be really exciting to see that in 2029. All right, so now we're going to shift gears. That was the last asteroid mission. There's another really cool mission that I'm currently working on, and this is a mission to Venus. So I've done a lot of stuff on Mars, got a couple asteroid things going on. This is the first time I've ever been involved sending anything to Venus, and it's very exciting. The mission's called Da Vinci. It's going to launch in June of 2029. And our goal with Da Vinci is to do a couple of flybys of Venus with the spacecraft and observe the clouds of Venus in the ultraviolet with our spectrometers and cameras, and then on the night side to observe it in the infrared, where we can look through some atmospheric windows and see all the way down through these thick clouds down to the surface. And in fact, the nighttime, it's so hot on Venus that even in the nighttime, the surface is over 400 degrees Fahrenheit, and it still emits plenty of infrared energy for us to be able to detect from orbit. And so we're going to do that during 2 different flybys. The first one will happen less than a year after launch. So 7 months after launch, we'll do this flyby. We do it again 17 months later. And then a little over 2 years later will be the highlight of the mission. That will be the release of this descent probe that will separate from the rest of the spacecraft and fly through those clouds, suck in material, study it as we go down, as well as take pictures of the landing site as we go down to the surface. So I have a little video to kind of give you a little idea about what that's supposed to look like.
It's 900 degrees hot at the surface, has powerful high-altitude winds, and is blanketed by a dense carbon dioxide atmosphere. The planet Venus. Although the same size and density as Earth, the similarities end there. Earth has water and light. Venus is desolate, dry, apparently lifeless.
The Da Vinci mission, named after Leonardo da Vinci, will now take us back to Venus and address unresolved questions about this mysterious planet. This exciting new mission will launch in June 2029. During 2 gravity-assist flybys, Da Vinci will study the cloud tops in ultraviolet light, tracking cloud motions and analyzing mysterious ultraviolet-absorbing chemicals. Both flybys will also examine night-side heat emanating from the surface. These geological clues will paint a global picture of surface composition and its evolution. 7 months after our second flyby, Da Vinci will release its atmospheric descent probe, which will enter the atmosphere over the course of 2 days. The probe will take about an hour to fall through the atmosphere, taking measurements down to the surface. These measurements will include profiles of composition, winds, temperature, pressure, and acceleration. Key gases will help us understand how Venus formed and evolved. Some of these measurements may even reveal signatures of ancient water. The spherical probe houses the state-of-the-art instruments that will work together to address questions about the Venus atmosphere, protecting them from the extreme temperatures, high pressures, and acidic clouds in the environment. Da Vinci's camera peers down through a small viewing port, and once the probe passes below the clouds, it will start to collect a series of 3-dimensional views that will also help us understand whether the rocks of the Alfa Regio Highland region reveal a story of an ancient continent shaped by water. And an oxygen-sensing student collaboration experiment will reveal the role of this gas in the deep atmosphere. The discoveries that emerge from this diverse data set will help tell us whether Venus was once habitable. And the story that we reveal will reach even beyond our solar system to analog exoplanets that will be observed with the James Webb Space Telescope. Venus is waiting for us all, and Da Vinci is ready to take us there and ignite a new Venus Renaissance.
All right, so that's Da Vinci launching 2029. We're currently designing and preparing that mission. A lot of fun to be involved with. All right, so I'm going to end the night kind of back where we started, back on Mars. talking about the Mars Sample Return Campaign. Now, it's called a campaign because it's not just a single mission. It actually involves 3 different missions. The first mission is the Mars Perseverance rover I mentioned earlier. So this launched in July of 2020. It landed on Mars in February of 2021. And one of its goals is to search its landing site. So it landed in a place called Jezero Crater. One of its primary goals is to look in that area and try and find the most interesting samples to bring back to Earth. And again, it's all about the water, or looking for carbon, or looking for organic material to talk about and address the life question. And so it's been doing its job ever since it landed. The second mission hasn't launched yet. We're still designing it. It's called the Mars Sample Retrieval Lander, and that's shown here. It'll launch in 2028. Its job is to collect samples from Perseverance and load them into this rocket called the Mars Ascent Vehicle. And the Mars Ascent Vehicle will launch the samples that Perseverance acquired into Mars orbit. The lander is also bringing along some backups. It's going to bring along 2 Mars helicopters, one of which is shown here. So you may remember, if you've been following the Perseverance mission, it brought along a single helicopter for the first time to prove you could operate a helicopter on Mars. Well, these helicopters will actually have a job to do. They'll be the backup just in case something happens with Perseverance and it can't either get the samples out of itself, it can't drive up to the lander. These helicopters will be used to go and retrieve the samples. The third mission of the campaign is the Earth Return Orbiter. That's shown up here. It never lands on Mars. It goes into orbit around Mars and rendezvous with the orbiting sample that will be in this payload up here. So it's going to rendezvous with it, capture it, process it, get it ready for return to Earth, and then put it into the Earth Entry System. And that entire spacecraft then will fly back to Earth and release the Earth Entry System, and these samples will land in the same place that the samples from Bennu are going to be landing, in the Dugway Proving Grounds in Utah in 2033. So here's what our first sample looks like. Perseverance acquired this in September of 2021. It's in this drill bit right here. So that's about the size of a large finger, like a fresh piece of chalk. And Perseverance can collect up to 43 of these. It took that sample and a second sample from this rock called Rachette, so you can actually see the holes that it drilled into that rock and extracted the material from that. And then most recently, it took 10 of its samples in these little cells and laid them very gingerly onto the Martian surface into a very easy location to get to. Just in case Perseverance has issues, these are the samples that the helicopters will go and fly to and pick up. All right, so to end the night, I'm going to show you a presentation, another short video that puts all that together to show you how it's supposed to work. All right, so here's the Mars Sample Retrieval Lander approaching Mars. Perseverance already busy doing its job, collecting samples. So if everything's working, Perseverance will drive up to the lander. It will load up the samples, and we can take as many as 31 tubes. Perseverance has got room for 43. So we can make a decision if they all get there, which ones are the most interesting. We're going to load them up into the rocket or the Mars Ascent Vehicle. So this doesn't go all the way back to Earth. This just goes into Mars orbit. So there's a second stage that puts us into a circular orbit around Mars. Then it releases the payload, or the orbiting sample, which we call the OZ for short. And the Earth Return Orbiter flies up, rendezvous with it, captures it, processes it, and puts it into the Earth Entry System. And then that whole spacecraft leaves Mars orbit, flies back to Earth, and then releases the Earth Entry System. And that's on its way to Utah. And it's actually not going to land using any parachutes. It's going to hit the ground at terminal velocity determined by the aerodynamic shape of that sample return capsule, which is pretty amazing. So that's all I have to show you tonight. I hope you've enjoyed it, and I think we do have time for questions. I'm not sure, Jack, how you want to handle that.
If you have a question, just raise your hand, and Dave DeBryan and I will hand you a microphone. I'll start with you.
Yes, two brief questions. First of all, regarding the Mars sample return mission and the samples that were left in that you described as easy to access place, how would they be retrieved if a windstorm or dust storm on Mars buries them in regolith? And the second question has to do with Bennu and the OSIRIS-REx mission, and that was, how was the landing site selected with regard to volunteers on the internet examining the images? Because I read somewhere that that was done, and I believe that there's a Discord server I'm on that is administrated or moderated by Dr. Pamela Gay of Southern Illinois University, and I was wondering if you have any knowledge of how that analysis by volunteers contributed to the selection of what landing site to fly to.
Sure. Yeah, thanks for your question. So let me handle the first one about Mars and these samples first. It is, in fact, that Mars sees dust storms, and like I mentioned earlier, these dust cyclones or dust devils on a fairly regular basis. If we left those there for years, yeah, then there's a potential that they could get covered up. But based on the length of the mission, that shouldn't happen. And also, we know exactly where the rover is on Mars. Even if they did get covered up, as long as the arm or the sort of the grabbers we have in the helicopters are strong enough, we could attempt, right, even if we couldn't see them, we would know exactly where they are and could fly to them. In terms of Bennu and trying to select the sample site, that is in fact true. We put all of our data out there to get help from just the general public to be sure that we hadn't missed something, right? Because we at the time of the operations of the mission, we were probably a group of a little under 100 people. Not everybody was even looking at the images. And obviously, these are very important. The mission itself cost about $1 billion, so these samples are billion-dollar samples. And so, right, that was an attempt to just get help from the general public to see, is there anything that we missed? Is there anything, just like Steve Metzger saw dust devils in the images from Mars Pathfinder. How long would have it taken for anyone else that was actually working the mission to discover that? So NASA always tries to engage the public, particularly where it could be useful. And in this case, we just wanted to make sure that we were leaving no stone unturned, so to speak. In the end, the site we chosen was the site that the lead scientists of the mission wanted to go to. But it did turn out it had the most carbon material, and it was also one of the safest places to land and not risk the spacecraft.
My question is, Bennu, the asteroid you said was an active one. Is passive the opposite of that? And what keeps that together? It was so dusty.
Yeah, so there's almost no cohesion, right? It's all gravity that holds this together. And in fact, we believe Bennu is just a smaller part of a much larger asteroid, and that there was a collision at some point. So it's likely that collision with whatever its original parent body with shattered almost everything in there, and then some of the material just gravitationally started to coalesce itself together. And so that's probably what happened with Bennu.
So also for Bennu, the sample collector, if it's going 2 centimeters every second, how did it make such a big, dust cloud? Yeah,
that's a really good question. So there's this thing called momentum. So even though we were going really slow, our spacecraft is really heavy. And so that's why there was a lot of energy imparted into the surface. So even though it was going really, really slow, it's kind of like if a big semi-truck would hit you going really slow, Even if it was going, maybe 5 miles per hour, you would definitely feel that. And so Bennu definitely felt us as we touched down, because we were still a really big spacecraft, even though we were going really, really slow.
So with the system to send the samples back up to orbit of Mars, how are they going to be able to test the reliability of that and be able to launch them up, get them off the ground and get them to orbit without losing those samples?
Yeah, so a lot of the Mars sample return campaign, the challenges associated with it are, how are we going to test all this out on the ground, particularly like when we rendezvous with that sample, that's going to be in 0G, essentially. So I'm not part of the rocket team. I'm not sure. There will be some testing. I'm just trying to find our Mars Ascent vehicle here. So this is being developed by a team at Marshall Space Flight Center. I'm not sure what they're going to do on the ground to prove this out. Obviously, they'll put a lot of redundancy into this as much as they can. It's a two-stage rocket, so you have to launch this one first, and then that second stage has to ignite. But I don't know enough about what they're doing on the ground to ensure it will work when it gets to Mars.
Okay, so you've talked about the missions that you were on, but what was it about being watching the planetarium that struck a chord in your young heart to seek out astronomy?
I don't know. So it was, it wasn't middle school. I was a second grader, and we went to the old location of the museum, and if you remember, they had another nice space display like they did there, and just something about it just grabbed my attention. And they had that old solar system there where all the planets would go around the sun at the right speeds, and you could see Mercury doing this and Pluto not moving at all. Pluto was still a planet back then. And it just engaged me. And then we walk into the planetarium and you're in this room, and all of a sudden they turn out the lights and it's nighttime indoors. How does that happen? And then someone starts telling you, oh, that's what that is. And you know what that really is? And what about if we got closer to it? What would that look like? It just grabbed my imagination. I thought, boy, that's something I would like to know more about. And so, as a kid, stuff kind of comes and goes. But this just never left me. And I was always interested in it. Every time we would go down to Florida, I'd have to go to Kennedy Space Center, to the point where my parents would just start dropping me off there and go to the beach. Well, I spent the day, with a pocket full of money, just, spending as much time as I wanted to on everything. And so it just never left me. I wasn't sure if I'd be able to find my way into working at NASA or even doing something like this. I didn't know anybody at the time doing that. Knowing that Roger Chaffee from the area, at least become an astronaut, gave me some idea that it was possible. And even though I went to grad school, the whole robotic program at NASA was a little dead at that point. And the shuttle was going pretty well at that point, and so we were launching humans into low Earth orbit. And it was really Pathfinder that kind of started all the robotic missions again at NASA, and getting involved with that was sort of my entry into getting a job at NASA. When they saw that on my resume, they were very interested, and I had some other opportunities to go into academia or go to JPL, which is a lab that NASA runs, but it's not NASA civil servants that work there. And I knew a lot of our people at Arizona would go on to JPL, because JPL is pretty much given the exclusive job of doing Mars exploration. They give us some of the Mars work at Goddard Space Flight Center, which is where I'm from, when necessary. So in fact, on board the ERO, the Earth Return Orbiter, our payload is a Goddard payload on there. But JPL is doing this. The European Space Agency is doing a lot of this. And like I said, Marshall Space Flight Center is doing that. So I don't know what it was about that particular winter day that I visited the planetarium, but it really stuck with me. And it's been great to be able to come back here and contribute periodically to hopefully ignite interest in some of the younger folks that are here, particularly the ones that weren't alive for all those 4 Mars missions that I talked about earlier.
Dr. Boss, what technology are you using on the surface for navigation? Here on Earth, we sort of take GPS for granted, but if you're parking these deposits out there, how do you get the helicopter accurately back to them?
Yeah, so something like Perseverance, the one really pretty just amazing thing is we have several assets, orbital assets, satellites around Mars right now. So the main way we navigate is through images. And we can see these things on the surface and reference their position with different landmarks that are well known and able to see on the surface. So that's, yeah, we don't have GPS yet on Mars. I bet we will before we send people there, because there's a lot of talk about, well, how do you make sure you keep a human crew safe? How do you help them navigate around? How do you help them plan traverses and EVAs and things like that? But right now it's using these assets that are in orbit.
Why didn't you suck up Bennu's dust?
What was the question, Jack? I couldn't quite hear it.
The question was, why didn't you suck up the dust from Bennu, right?
Yeah, so we were operating in a vacuum, so there was nothing to suck up. We had to like push out. So we had to bring our own, essentially, oxygen, although it was nitrogen in this case, and we pushed stuff into the inside of that sample head. So a vacuum cleaner wouldn't work. It's already a vacuum in space, so it wouldn't have worked to collect a sample that way. Going back there.
With the, can you go back to the 2029 mission slide that had all the circles on it?
The circles?
The sample mission.
Oh, sorry. The little cells, this one?
No, what was it? It was the, I'm sorry.
There was a lot, I know.
Yeah.
Do you know which mission?
The graph. It was a graph of a couple different.
The Apophis.
Yeah, Apophis.
Yeah, that's a really busy one. We could spend probably a half hour going through it. But so yeah, go ahead. Sorry, ask your question.
Are all of those circles different missions or different asteroids?
These were this gives you a little bit of idea. If Apophis would hit us, how much energy would be released compared to some other asteroids that actually have hit us. So here you can see Tunguska. That was the asteroid that hit us, or hit the Soviet Union back in sounds like someone knows about it. So yeah, so this was Tunguska. Also, you might remember Chelyabinsk. So there was this asteroid or a meteorite that was captured on tons of cameras in the Soviet Union from cars because they have this huge insurance fraud problem there. So they were able to reproduce the trajectory of the Chelyabinsk meteorite. So that's shown right there. So you can see if Apophis would hit us, it'd be a big deal. That's what these different sort of circles are meant to show. And then these I was talking about earlier. So here's the Roche limit. So this is if Saturn has a ring because it has solid bodies that got within its Roche limit and broke it up. That's why those rings are just these little particles. Apophis doesn't get quite that close from an Earth perspective, but it does get to what's called the resurfacing limit that Binzel et al. Published in 2010. So that's why we think Apophis is going to look different after it flies by Earth. And we haven't ever been able to observe something like that before.
Okay. I did have one other question.
Okay, go ahead.
With the Mars sample return rocket, you mentioned that it ejects a payload as a two-part rocket. Are we worried about the second part contributing to any sort of either space pollution or even being in the path of the spacecraft?
Oh, no, it'll be such a small amount. It probably won't even be on the same path by the time that orbit evolves. Yeah, that shouldn't be an issue.
Cool. Thank you.
So for the return to Mars mission with that payload that's going to come back to Earth, you said that it was going to hit the ground at terminal velocity and it wasn't going to have any parachute. Would you know exactly how fast that would be, and how would you prepare the capsule for an impact like that?
Yeah, so if you could look on the inside of what they're designing that thing to do, it's pretty amazing. It's like, this mega four-wheel drive type suspension all on the inside of that thing. I don't know what the velocity is that shape will generate. The reason we're doing that is because, so I didn't talk about this at all, but right now this is a huge deal in Mars Sample Return Campaign. And it's all about how do we know these samples are safe? How do we know that we're not going to contaminate Earth with something that's going to go crazy and it will make COVID look like child's play? So the reason we're not using a parachute is because parachutes, you can't make all that reliable. They're really good, and in most cases, they'll do just fine. And so the folks that were designing that, or that entry system, one of their requirements was you have to survive if your parachute doesn't work. So they're building this mega system, right, that can absorb hitting the ground at their terminal velocity. And then, a couple of weeks go on, and they said, well, if we got to do that anyway, why are we even going with a parachute? And so that allows us to use that mask we would use on a parachute system for something else that we need to use it for. So that's why it's a different delivery than what we're using with Bennu, just because we have to keep those samples safe. And in fact, it just glosses over that in the video. A lot of the processing inside of the Earth Return Orbiter in the capture containment return system is actually sterilizing everything that we capture. Everything on the outside of that it was going to be heat, and as of 3 weeks ago, due to some work actually my team did, we proved out you can actually sterilize it using ultraviolet light at around 275 nanometers. So this will be like putting whatever hijacked its way along on the outside of the surface, whatever's contaminating it, with about 4,000 years worth of Martian sun. So it should kill anything that might be alive on Mars and would exist or contaminate the outside of the surface of the orbiting sample. Yeah.
And then I have one last question. From the standpoint of, for example, a high school student, what would you say is the best way to go forward, or the best decisions and process of getting a career in something like aerospace engineering or working for NASA?
Yeah, so I definitely continue doing your best in all your studies. There's no doubt you got to do well in everything to get into a good program, but it's obviously the math and the science. And then for undergraduate, it's not as important as where you decide to go to graduate school. You really want to go somewhere that's actively involved in this work. So when I give talks to students, I tell them, when you're looking at graduate schools, don't pay any attention to that, like US, World Week, whatever, the rankings that come out periodically for schools. What you have to do is you have to read the literature, and you look up, okay, where are those authors and where are they from? If they're from academia, that's where you want to go, because that's where the work is being done. And so that's why I went to Arizona. That's why people go to Arizona State. A lot of the sort of the big names you would think of, there are a lot of really smart people there, but they're not building hardware. They're not actively operating spacecraft. So right now, Arizona is still a really good place to go. Arizona State's a really good place to go. Caltech, of course, because they're associated with the Jet Propulsion Laboratory. And that's really, this whole community knows each other really well. We all, a lot of these pictures, you saw some of those people in the background, they're involved in multiple missions, like Eileen that was in that heartbreaking picture with me. She's been involved with multiple missions. Usually it's the same group of people that are coming together, so it's kind of a small community. So you just want to get into that community. And unfortunately, it's not always just what you know, it's who you know. People are comfortable, like, oh, this person knows what they're doing. I've worked with them before. So look for those opportunities. And of course, we have internships at NASA as well. That's a really good way to get in once you've either had your undergraduate already or you're working on a graduate degree. That's mostly how we do our direct hires now that become civil servants immediately. There are people that are getting their masters or their PhDs. We still hire some bachelors as well, but it's becoming more and more rare. It's almost everybody now. It's, around the table, it's doctor, doctor, doctor type thing. But that's a really good way to get in is to do an internship.
Yeah. Dr. Boss, I just want to preface this question by saying that we're all friends here, and I'm sure that nothing you say will leave this room. But do you have any thoughts about the manned versus the unmanned programs in terms of cost, risk, and potential?
Well, I'm a big believer in the human program, but we can do so much more things with robots that you wouldn't dare do with people. So I probably should have said that up front. These are all robotic missions. Every now and then I'll give a talk and people ask where the people were inside some of these things. These are all robotic missions, and we would never dare do things that we do with these robots that you would with a human crew. But to me, space exploration is much more than just science. The science is interesting and it's important, but our ability to put people out there to make us a multi-planet species is really important, at least from my perspective, because eventually Earth is going to get knocked out, and we also have to look for other resources. The asteroids could be a good place for resources. So I don't really see a competition. Obviously, the cost is a whole different order of magnitude. These missions are typical. So the Mars sample campaign will probably be about $6 to $7 billion when it's all said and done. James Webb Space Telescope was a $10 billion mission. Almost all the other missions I talked about were about $1 billion a pop. Some of them are a little bit cheaper. But something just like a single shuttle launch was over $1 billion, even amortizing the cost from development all the way to the end. So you can do things a lot cheaper, a lot less risk, but I still think it's important to show that we can successfully live and work and eventually thrive in outer space. I just think it's important to our species. So I don't see a conflict between them, but yeah, you definitely approach them differently.
Sort of bookending this here. What is the distance that Apophis will approach Earth relative to Earth's diameter? Because the graphs show, like, relative to the distance of the orbital radius of the Moon, what would it be in Earth radii? Do you know?
I'm not sure off that, but you can do the math. It's less than 20,000 miles. Google the diameter of the Earth and do the math. You can figure it out. Anything? Is that it?
I think that's it.
So before you leave, so each of the current projects asked me to bring along some goodies for you. They're up here at the front. Feel free to take one or two, whatever you would like, especially the kids, and be a little memento for you for the missions that we're working on. And yeah, pay attention September 24 when we bring those samples back from Bennu.
One more round of applause.